Imagine walking through a field where instead of just one hill or one valley, you have multiple hills and dips created by different mounds. That's exactly what happens in electrostatics when we deal with more than one charge. Each one contributes to the overall electric potential. Now here's the cool part. Unlike electric field, which is a vector and needs directional consideration, electric potential is a scalar. That means we can simply add the potentials from each charge algebraically. So, if you have several point charges Q1, Q2, Q3, and so on, placed at different locations, the total electric potential at a point P is given by V equals V1 plus V2 plus V3 and so on, which becomes V equals summation of 1 by 4 pi epsilon naught multiplied by Qi divided by Ri, where Qi is the ith charge and Ri is the distance from point P to that charge. This is called the superposition principle for potentials, and it holds true regardless of how many charges you're dealing with. You'll see this principle applied again and again in molecular physics, electronics, and field mapping.
Alright, let's formalize what we just discussed using a bit of math. Suppose you have n point charges, which we label as Q1, Q2, all the way up to Qn. Each is located at position vectors R1, R2 through Rn. Now the potential at some observation point P due to one single charge, say Qi, is given by Vi equals 1 by 4 P epsilon naught multiplied by Qi divided by Ri. Since potential is a scalar, we apply the superposition principle directly. So the total potential at point P becomes V equals summation from I equals 1 to n of Vi, which is V equals 1 by 4 pi epsilon naught multiplied by summation of Qi over Ri. What's beautiful about this is it doesn't matter where those charges are placed in space or whether they are positive or negative. You simply plug in the distances and signs and sum the results.
Let's take a special case, a classic configuration known as a dipole. Suppose you have two charges plus Q and minus Q placed symmetrically along the x-axis, separated by a distance of 2a. Now we want to calculate the electric potential at a point P that lies somewhere in space. Using the same superposition idea, the potential at point P is V equals 1 by 4 pi epsilon naught multiplied by open bracket Q divided by R plus minus Q divided by R minus close bracket. Here, R plus is the distance from point P to the positive charge and R minus is the distance from point P to the negative charge. Now, if point P is very far from the dipole, meaning the distance R is much greater than A, we can apply binomial approximation. The expression simplifies to V approximately equals 1 by 4 pi epsilon naught multiplied by P cosine theta divided by R squared, where P is the dipole moment given by Q times 2A, and theta is the angle between the dipole axis and the position vector. So what we see here is that a dipole is just a special case of a system of two charges and it obeys the same rules, just with some elegant simplifications.
Let's now visualize what this all means in terms of space. When you have a single charge, the equipotential surfaces are spheres centered around the charge. But in a system of charges, especially more than one, these surfaces bend, twist, and stretch. Why? Because each charge is pulling or pushing on the potential field in its own way. These surfaces are where the potential value remains constant. So if a test charge moves along them, no work is done. Understanding these surfaces is not just theory. They help us predict how electric fields behave in complex situations, such as inside capacitors, molecular dipoles, and even around neurons in the brain. As you'll see in the diagram, these equipotentials for two opposite charges look like banana-shaped loops, distorted by the push and pull of both charges.
Let's solve an advanced level example to tie this all together. Here's the problem. Three charges are placed at the corners of an equilateral triangle of side 1 meter. Q1 equals plus 3 microcoulombs, Q2 equals minus 2 microcoulombs, and Q3 equals plus 1 microcoulomb. We are to calculate the net electric potential at the centroid of the triangle. Step 1. In an equilateral triangle, the distance from each vertex to the centroid is R equals 0.577 meters. Step 2. Use the formula for each potential. Vi equals 1 by 4 pi epsilon naught multiplied by Qi divided by R. Now plug in the values. V equals 9 into 10 to the power 9 multiplied by open bracket 3 minus 2 plus 1 close bracket times 10 to the power minus 6 divided by 0.577. That simplifies to V equals 9 into 10 to the power 9 multiplied by 2 into 10 to the power minus 6 divided by 0.577. The answer comes out to be approximately 31,200 volts or 31.2 kilovolts. So, the total potential at the centroid due to this triangular system of charges is 31.2 kilovolts. Let's quickly revise what we've learned about the potential due to a system of charges. First, electric potential is scalar, so we can directly add contributions from multiple charges using the superposition principle. The general formula is V equals 1 by 4 pi epsilon naught multiplied by the summation of Qi over Ri, where each Qi is a point charge and Ri is its distance from the observation point. This formula holds no matter how many charges we are dealing with or where they are located. We also saw that dipole potential is a special case of this general formula, and the idea of equipotential surfaces helps us visualize complex field interactions. And finally, in a numerical, we saw how easily this principle lets us solve real charge configurations, like a triangle of charges. This knowledge is not just academic, it's used in molecular bonding, circuit design, medical imaging, and field analysis tools in engineering and neuroscience. I hope you now feel confident in dealing with systems of charges and the potentials they create. See you in the next session with another beautifully connected concept in physics.